Study on Motion Tracking Control System for AGV. This paper presents an automatic guided vehicle, AGV, motion tracking control system. With the application of new control algorithms and the development of electronic technology, AGV is developing toward high speed, high precision, openness, intelligence, and networking, and it also puts forward higher requirements for motion control systems. To realize high speed and high precision position control, AGV must rely on advanced control strategies and excellent motion control systems. In this paper, according to the requirements of the control system, the Arduino/51/STM32 microcontroller is selected as the core to design the motion control system. The paper studies the automatic guided vehicle motion tracking control system. The simulation of the motion tracking control of the intelligent robot is performed using MATLAB/Simulink. The Simulink model as well as the graph showed the AGV can reach the moving goal successfully. Keywords: automated guided vehicle, AGV, motion tracking control system, obstacle avoidance, Simulink model, PID controller. Introduction. AGV is an automatic guide vehicle. It refers to a vehicle equipped with electromagnetic or optical automation devices that can travel on the road with safety and various transmission functions. An automated guided vehicle is a programmable mobile vehicle that follows marked lines or ground wires. Automatic steering vehicles are robots that run on the floor of a facility run by a combination of software and sensor management systems. 1. AGV is a mobile robot that follows a specific path in the ground. They are the most widely used unmanned aerial vehicles in the industry to move materials around a manufacturing facility or warehouse. AGVs are used in almost every industry: pulp, paper, metals, newspaper, and general manufacturing. Transfer of material or finished product and storage in bed is one example of the use of AGV in factories. 2. The AGVs, automated guided vehicle, began as transport devices developed to assist the manufacturing system. In the industrial robotic field, they are defined as transport vehicles driven by a computer system with different mechanical configurations. Earlier inventions on AGVs can be dated back to Barrett Electronics in 1953. One of the oldest publications on AGV can be found in. It is used to distribute materials in warehouses and to move and operate in production facilities to production areas and storage areas. It consists of different components like cranes and hoists, elevator and lifts, conveyors, robots, automated storage and retrieval system, as/Rs, and so on, which are focused on the process of transferring something from one place to another. Utilization of components, either individually or from a combination point of view, is determined by its application or pre-assigned flexibility. Tracking is one of the most important aspects of AGV control and a prerequisite for completing accurate road tracking work. However, AGV is very indirect, making it difficult to track control challenging. 3. Many methods were proposed to solve this problem. 4 and 5 proposed a linear proportional control method, 6 proposed a PID control method. This intelligent handling robot is based on the Arduino/51/STM32 microcontroller board program, to design an aluminum alloy body, multiple mounting holes on the robot chassis adding various sensors and controller. A space for the servo is also left to turn the mechanical manipulator. With the help of the engine, the robot chassis can turn smoothly to the left, right, circular, forward, and robot backward, etc. The size of the robot body part is 290 mm length, 520 mm height, and 260 mm width in thickness, where it adopts intelligent bus servos, and supports various controls. Metal gears and imported potentiometers are mounted on the arm of the robot, and the robot has 6 degrees of freedom robotic arms with every joint controlled separately. Obstacle detection. In a real environment, an automated guided vehicle must avoid obstacles to go to or moving to a target. Depending on the positions of the target or the goal and the obstacle, relative to the automated guided vehicle, as the automated guided vehicle moves toward the target and sensors detect obstacles, it is important to control the avoiding strategy and motion control of the speed. In this paper, we use color recognition sensor to the intensity of light reflection by different colors, single track sensor used to when the detected object appears within the detection range, the infrared ray is reflected with sufficient intensity and the infrared receiving tube is saturated. Sound sensor is the most sensitive and used to detect ambient sound intensity. Ultrasonic sensor protecting the automated guided vehicle robot from hitting the wall, and measures the distance from the wall or other obstacles as close to the measured distance the motion control will achieve its intended goal by looking for an alternative route. 7. Kinematic model. In this paper, autonomous guided vehicle robot platform considered is like a monitored mobile platform which is driven by using 2 motors while 2 standard Caterpillar tracks operated by the actuators for the motion of the mobile robot, and they are placed on both sides by a mobile robot. The kinematic mode can be described as shown in Fig. 1. After tracking the speed of an automated guided vehicle, the next behavior that can be evaluated are the local coordinate of the tracked and automated guided vehicle robot and longitudinal and lateral motions during movements. Both longitudinal and lateral motion is described as follows. 8. The center position, X, Y, and orientation of the AGV are represented by of the automated guided vehicle robot during traveling need to be defined as C is the center of a robot mobile platform. L is the length between 2 tracks, VL and VR denote the linear velocities of left and right track relative to the ground, respectively. It can be calculated from the equation of the left velocity, VL, and the right velocity, VR, of the tracks are written as. Dynamic modeling of the robot is the study of motion in which forces and energies are modeled and studied. The actuator modeling is required to find the relationship between the control signal and the mechanical system input. The motion control system of an autonomous guided vehicle can be simplified to a DC motor motion control. In modeling DC motors and in order to obtain a linear model, the hysteresis and the voltage drop across the motor brushes. Simulation. It is important to know the characteristics and specification parameter of the autonomous guided vehicle robot system and the DC motor to control the motion of the robot according to the speed at which it is considered as the desired linear speed. Motion of the AGV robot is 0.4 m/s when 7.4 V input is embedded to the robot for supplying electric power. Using the transfer function equation we can get the speed sensor constant value as follows. Fig 5 simulation result of motor with Kp equals 1 key equals 0 and Kd equals 0. We can see the result of the simulation in Fig 5. Indicates that the AGV robot linear speed is equal to 0.1306 m/s. When it is compared with the desired robot linear speed, there is a difference or an error of 0.2694 m/s. Therefore using manual tuner PID controller should be used in this paper to reduce this error. Second, we want to use the manual tuning method of PID controller to get the desired speed effectively with K9 equals 157.18, key equals 86.22, and Kd is 21.68. We can see the result of the simulation indicates that the automated guided vehicle linear speed is 0.4 m/s with a little bit overshoot, and it has. The robot platform we are doing with autonomous guided vehicle robot which has two driving DC motors as shown in the Simulink model of AGV robot system figure 4. We have already done the Simulink for the DC motor and running the model will get the result in the figure 5. First of all, we want to test the Simulink model of DC motor with the wheel for setting the parameter key and Kd gains to 0 and then increase the value of Kp gain until the loop output becomes to oscillate. Kp equals 1. Key equals 0 and Kd equals 0. The result of the simulation indicates the robot's linear speed is not stable. When it is compared with the desired robot linear speed there is an error as shown in the Fig 5 as the simulation result. Conclusion. In this paper, an automated guided vehicle has been controlled of the independently driven wheels is based on a kinematic model and dynamic model. An automated guided vehicle robotic platform and kinematic based on a motion tracking system are designed. The DC motor Simulink modeling is tested based on DC motor parameters and PID parameters. To reduce the error, the DC motor speed is controlled by the PID controller for the AGV motion control system to the desired linear speed in a robotic platform. After controlling AGV speeds, it can move forward, backward, right, left. We have used different sensors to track the tracking control system and avoiding obstacles. In the future work, there are many tasks to be considered. The goal-seeking issue, GPS can be used to find the current coordinates and assign to desired goal position coordinates. Accurate control of the heading angle and orientation can be performed using a magnetometer.